Okay. Very good evening, everyone. Myself, Dr. Ajay Kumar. I am Executive Director and founder of SARA Institute of Data Science. And our mission is to take data science knowledge to each and everybody and make it more inclusive. And to complete this mission, every year we conduct a summer school using our language. And this year we are conducting our second summer school. And it is happening in India, near to Delhi. And today is the fourth day of our summer school. And we are very proud and happy to have Dr. Lito P. Cruz with us today, give an expert lecture about hypothesis testing and regression for forecasting. So Dr. Lito is a data scientist with an experience of 25 years working with international organizations, private companies, as well as consultancies. And I approached him, and he humbly accepted our invitation, and he agreed to give a pro bono talk and a tutorial session to SARA students for this summer school. So thank you, Dr. Lito, for accepting our invitation. And now I welcome you to start your session.
Okay,
Please.
thank you for inviting me. It's a pleasure to give a lecture on statistics, testing of hypotheses, and also the statistical aspect of regression testing. So, regression for forecasting, I should say. So, information about me is can be found in LinkedIn. Um, so the last 10 or 10, at least 10 years, I've been doing work as a data scientist. I was a senior data scientist for a couple of uh, companies and the government also in Australia. And I led teams, several teams. I mentored several data scientists. And today I'm back doing consulting work. I go to a client and work with them for a couple of years. And then I hop on to the next one. So um, there was a time when I was also teaching. I was teaching for Monash University for a couple of years in their statistics, business statistics side of things. So what I'm going to teach you today is gathered from my experience of teaching statistics to especially business students, as well as science students too. So I was teaching for the Faculty of Business at Monash and also for the Faculty of Sciences, specifically in the mathematical science department for a while. So okay, um, this uh, in, carries a little bit of uh, some high school knowledge of statistics and some high school level, maybe year 12, year 11, year 12 kind of discussion. So, but I will go back to the basics until we get to the building the topic of hypothesis testing. So if you have any questions in between, um, you know, raise your hand and I'll or type it into the chat as I'm progressing along, and I'll pause for a moment and try to answer that question. Okay. The first one is, as you can see, we look at statistics as the science of collecting. It's called, this is a standard definition, the process of collecting, analyzing, interpreting, and presenting data. And that's a very broad, those are very broad characteristics of statistics. But the main point is really drawing conclusions from data with the aim of having informed decisions and making effective policies. That's the whole point why we collect data, analyze it, interpret it, and present it so that we can form an intelligent decision uh, and effective policies. Now, this informed decision is contextualized or effective, and as well as effective policies, I should say, are all contextualized in a problem situation, in a research question. And typically, the research question would like to solve a problem from a business context. At least we want to know whether this is a good decision or bad decision, whether we should cause these policies to um, be constructed or implemented or not. Okay, so an example would be uh, assume that you're a bottler like Coca-Cola, and your machine you want your machine to be accurate when they're dropping Coca-Cola soda into a can of 350 ml or a bottle, which is let's say 350 ml bottle. You want it to be at the set size, okay, a set volume. Now, if your machine is producing more than what the finance said that your price should be, uh, you're only say you're charging it only for 300 ml, but your machines are producing 350 ml. So you're exceeding by 50 ml. You're giving away this 50 ml for free. Okay. In other words, on the other hand, if you're advertised that your vending machine or your bottles that you're selling is set to 300 ml, but you're only selling it, but you're only giving 250 of it or 257 of it or 280 of it, so much so that it's not obvious to the customer, but eventually if somebody tries to study whether you're giving the right amount, then that would spill distrust from your customer. They say, well, wait a minute, I'm paying this much amount for this Coca-Cola bottle, and it's not even giving me what it advertised. So both of these are detrimental to the company. The company will cost them more money and only charging for 300 when in fact they're producing 350. On the other hand, they're getting more money for 250 ml, but the customer can find out and say, well, that cannot be trusted. The reputation of your company can go down. And when in the business world, when trust is no longer applicable, you lose business. Okay, reputation has got a lot of it. So this is where statistics can help you make sure that it helps you measure things. So we use mathematical and computational tools for the above purpose of decision making and policy making. And the field where this is used, I mean, these are only typical ones. You can in medicine, biostatistics is very important and a very I say to my colleagues that in biostatistics you get the whole um, discipline of data science in action. You see all of them being used there. So it's medicine, social sciences, um, social studies, political studies, um, in business, of course, economics and finance. Also in engineering and hard sciences, the physicists use statistics as well, especially astrophysicists, and of course the government, because the government establishes policies, and so they like to measure whether their policies are doing what it's supposed to do. Does it increase revenue? Does it increase GDP? Are people satisfied because of their taxes, etc.? So with statistics, we have several kinds, branches. One is the descriptive part, when we characterize the behavior of the data under study, and the inferential part. This is where we make conclusions from part of a sample data to the whole of population data. Okay, so the idea of a sample and idea of a population, they are very important concepts, because in statistics, what we do is because we cannot examine all of the population, due to logistics problems, time, money, and so on, practicality, we cannot um, study all of them, get the data of every aspect of a population. We have to settle with a sample, and a sample, of course, is just a small image of the bigger bigger picture. And obviously, if we try to judge the population from the sample, it will not always be 100% accurate. Nevertheless, our description of the population, which we got from the sample, can still be useful. Okay, it can still be um, materially useful, and we don't have to discard it because it's not the whole population that we're talking about. So you get the advantage and disadvantage of doing population work versus sample work. Okay, most of the time nowadays, the good news is because the computer nowadays is very fast and can accommodate big data, lots and lots of data. Most of the time nowadays, people tend to no longer sample. It depends on your problem. Okay, they tend not to sample anymore. They just go to the whole population. I'll give you an example. If I'm a bank and my study is my customers, my depositors, okay, then I can have access to all of my depositors because they're in the computer. I can study the whole population. I don't have to do sampling because my computer is fast. It can accommodate large uh, storage. It can store all of this people's information there, and I can pass through them. Okay, so and I don't have to wait a lot of times. Okay, to do this. So that's where sampling is not needed. On the other hand, if we're going to do some interview people that we have to go down to the population and find out for every individual, um, let's say we're doing a study of people's educational background, okay, of our country. Well, if our country is composed of let's just say it's composed of just 10 million, okay, you cannot go down to every 10 million, every part of that 10 million, every individual in that 10 million, and ask for their salary um, range, for example, or their educational background. You can't. It's basically impossible. It's hard. By the time that you needed to make a decision to make a policy regarding the education of your population, the research principle is probably would probably have died already. How many? Because it will take years in order for you to go through every member of that population. So what you're going to do is you're going to sample only because of practicality. You will just go to sample, and based on the sample that you have obtained, you will make decision or you will make generalize what you have found in that sample to the whole population. It will not always be 100% accurate, but nevertheless, you like it to be close to the um, true measure that we're trying to measure. All right, so just a background there. Some may see the statistical method as the same as research. So I have a question for you. Can you spell out what are the similarities and difference between research and the statistical method that we did? Okay. For example, in relation to this, this is some reflective question. I'll give you about a minute or so. If you have anything, you can type it here. I don't know. Are they allowed to say something back, Dr. AJ? Okay, maybe if you're not allowed yet, you can just type in your answer there. What do you think is the difference between, let's see, or similarities difference between the statistical method and the research process?
Actually, we were not able to go through the statistical analysis much We just able to cover the exploratory data analysis and
Okay.
not beyond that. And it's a little explanation how to frame hypothesis. Just that's it. We could not
All
cover
right.
today. Yeah, sadly.
All right. So, well, the way we'll answer this is that the statistical method and the research process are the same. They're similar. Um, the similarity is that in the research method, you can also collect, analyze, interpret, and present data. So basically, statistical the research method in the statistical process or research process and statistical process, there is an overlap that happens, a very big overlap that is present between the two of them. And both are doing the same thing, collecting, analyzing, interpreting, and presenting data. That's what research does. Okay. And then making conclusions based on the study. So part and parcel of research is the use of statistical method in research. Uh, Now, especially that is a quantitative approach to a research question. Of course, there is also the qualitative approach to a research question. Um, and if your research is in the field of history, for example, or something in the past, then maybe statistics may not be appropriate. It depends on the question that you're answering. So I have here, do some browsing on the nature of analytics and the statistical method, share your findings in class. So maybe that's something that you can uh, take a look at later on after we finish, and uh, something that you can um, uh, reflect on after class. Okay. Okay, so one aspect of uh, that we have to deal with is the nature of uncertainty. Uncertainty pertains to our lack of knowledge of how a phenomenon can happen or how a phenomenon works. There's a lot of uncertainties that we deal with every day. For example, we're not so sure uh, as to if there might be a weather forecast for our city that today is going to rain. Okay, but we're not exactly sure. How sure are we that uh, that part of the neighborhood where I'm going to be, is it going to be rain there? Okay, so most of the time we can find out now, but sometimes they don't also work. Okay, it's because there is some uncertainty. Uncertainty is a part of our life here on Earth. Uh, so, will an event happen or not? That's something that we like to ask. And the reason why I'm talking about uncertainty is we're going to talk about probabilities, and probabilities is captured or is considered in statistics. So, for example, how likely will we get such and such an event? For example, these are uncertainties. Is the moon made of cheese? How likely is it made of cheese? These are silly questions, of course, but it illustrates the nature of uncertainty. For example, can I get the ace of spades when I draw a card from a card deck? A card deck has got 52 faces, values. You have the spade, you have diamond, you have the club, and you have the heart. Okay, so when I draw one card from a deck, what's the likelihood that I will get a spade there? Okay, so that's a kind of example of uncertainty. Uh, so it's best to measure the likelihood of an event occurring. So, and here we use probabilities. We can use the idea of probabilities here to be a gauge that quantifies the certainty or uncertainty of an event occurring. For example, what's the probability having rain tomorrow? Okay, so if you go to some um, weather if, uh, uh, apps, applications, you will see that they have they do it in percentage. You have 64% of rain today. Okay. There's a 64% chance of rain. And subtracted from 100, you have 36 percent of not raining, in other words. So for example, let's look at the idea of tossing a die. A die has got 6 faces, number 1, 2, 3, 4, 5, 6. We can get either one of them as a possibility. Okay. Total-wise, there are 6 possible ways when we toss it once, right? When you toss it once, you can either get 1, 2, the phase 2, the phase 3, the phase 4, phase 5, or phase 6. Okay. This is assuming we have a fair die. Okay. We have this idea of percentage as probability. So an example here is that this is just giving appreciation of probabilities. Okay, so here the normal way of measuring a probability of an event happening is E stands for the set of possibilities for an event, and N is the total of all event possibilities. For example, for the die that we're throwing, there are 6 possibilities. The total way of getting one of them, okay, is 6. Either you can get 1, 2, 3, 4, 5, 6 the first time we toss it. So N there is 6. Well, if you ask me, okay, what's the probability that when we toss a die, we will get a 3? Well, there's only one way of getting a 3, and that's getting the 3 face. So there's only 1/6 way of getting a 3. But if the question is different, if the question is, what is the probability when I toss a die, I'll get an even face? In other words, I could get 2, 4, or 6. Well, there are 3 possibilities, 3 ways of getting an even face die when you toss it, right? I could get a 2 or a 4. There are 3 ways of getting a face when you throw a die. So that would be 3/6, and therefore the probability percent, or 1/2. Do people agree with that? You can. Are they allowed to answer feedback questions, or just a feedback to know whether they understand what I'm saying? Maybe they can put uh, a thumbs up, if they understood what's happening there. So going further, say instead we are interested in the event of us getting a 2 or 5. Well, there are only 2 possibilities of getting a 2 or 5. Thus, the event we're looking for in a toss like this is where A equals 2/5. And the probability of getting a 2 or 5 is 2/6, which is 1/3. So that's how you measure probabilities, okay? Now, why we're talking about this is we're talking about this so-called probability distribution. How is the event, how are the numbers or the values of probability distributed? How does it, what's the characteristics of your event, basically? And the probability distribution in a way tells you how this event question. Okay. This means that there are infinitely many values in a specific range or interval. In that interval 16 to 20, there are infinite number of values there. For example, I can get 16.01 degrees Celsius. I can get 16.0102 Celsius, 16.0103 Celsius. And I hope that illustrates already what we mean by continuous probability. Okay. This means that there are infinite many values in a specified range or interval. So to ask what is the probability that we will get 16.2345 Celsius tomorrow at 3 p.m. is 0. Okay. It's practically 0. Okay. Because that's a line, one line in the range of possibilities, which is infinite. So of course, 1/infinite something. What's the answer? 0, isn't it? If I divide 1 divided by a very big value, let's say 1 over 3 million, for example, it's almost zero, isn't it? You look at it, uh, it's almost zero. Okay, so that's why if you in a continuous probability distribution, asking it for a particular value is almost zero, but you can intelligently ask it for a range. Okay, what's the probability I'm going to get 16 to 20 degrees Celsius tomorrow? That will make sense to the weatherman. Uh, so, so here's an example. You arrive at your office and you take an elevator to your floor and say it's known that the elevator can arrive between 0 to 50 seconds upon pushing the button. This is called a continuous uniform distribution and can be modeled by the probability density function, which is here, which is this one. Okay. Um, so if you say to me, what's the probability that I'll get uh, that in 10 to 20 seconds, an elevator is going an elevator is going to stop uh, at my floor or on my floor. Well, uh, you do this. Okay, this is called continuous probability distribution, and it's also uniform because um, it's not that behavior is um, very constant, somewhat constant, you see. So here, for example, the question is X, here is the event that we are going to get an elevator within a certain number of seconds. Now, if it's known that the elevator can arrive between 0 to 50 seconds, then we can ask the question, what's the probability that I can get it from 10 to 20 seconds? This is a question now, okay? All you do is you say 20 over 10 minus 10 divided by 50 minus 0 is 1/5. They've got 20% chance. You will get an elevator on your floor in 10 seconds time. Okay? This is 10 seconds, It's basically 10 seconds time. So it's the same, okay? Of course, in 0 to 10 seconds, it's the same. Yes, okay, I'm going to go now to the hypothesis uh, checking, okay? Uh, so I'm just leading up to I'm just leading up to the idea of probability distribution, because if they don't know probability distribution, then the hypothesis testing may not be very easy to grasp. And so I'm going to first talk about the hypothesis testing, sorry, the normal distribution, and then go to hypothesis testing. Or do they know about probability normal distribution already? Do they know this? Okay. Let me go to that now, okay? Uh, there is a probability distribution called the normal distribution, and you will need this in hypothesis testing. You need to know this so-called distribution. This is how your data behaves. This is basically the bell curve. Okay, so this is found in nature. The normal distribution is found in nature. And a lot of phenomena that we have seen in the world is governed by the normal distribution. Most likely, it's governed by a normal distribution. There are many distributions around. Okay, there is the exponential distribution. There is the gamma distribution. All of this distribution, but we don't need to know all of that. We only need to at least know what a normal distribution is. So a normal distribution is specified by uh, a mean and a standard deviation. Okay. This is where comes into play. Okay. Normally they notate it by saying x tilde n mu sigma. Okay. So mu would be the mean of that distribution, and sigma would be the standard deviation of that distribution. Do people know what I mean by mean and standard deviation? Can give me a thumbs up or no, and I'll review you. Let me know if you so the normal distribution is the most helpful one. Uh, uh, there is also a theorem that even if you do not have normal distribution of a phenomenon, it's not normal. All you have to do is get its corresponding mean, keep on doing some sampling on it, and that sample mean that you get will be normal. Okay, that's why it's so powerful. This normal distribution is so powerful. Almost you don't need to know a lot of things except the family of normal distributions. Okay, how does it look like? Well, this is what they call the bell curve. Most of the time, your data is packed within the center of that uh, that curve. In other words, if you do a histogram of the way your data works, for example, let's look at the ages of people who are going to university. Now, would you see students in a university who's got an age of 85, for example? Would you see a lot of them there? Yes or no? I ask you a question. If you were observing universities, would you see a lot of people, senior citizens, studying in a university? Would you see a lot of them? What would be what would you answer? No, correct. You won't see a lot of them there because, of course, their age, their grandparents, they don't have any more energy or ambition to study because their grandparents, they're taking care of kids. And so, okay, on the other hand, would you see a lot of uh, people with the age of 13 and below studying in the university? Will you see a lot of them? Yes or no? No, okay, correct. We don't expect um, uh, children age 13 or 15, most of them studying in the university, taking a degree, correct? Okay, but would you expect people with the age of, let's say, 18 to 25, would you see a lot of them in studying in the university? Yes, correct. Yes, very correct. And so when we say that most of them, this is your bell curve. This is where your when you try to graph the number of people with this age studying in the university, you will see that a lot of them, the highest peak that we'll get is those people whose age is probably from 18 to 25, because these are the normal university number of people whose age is 18 and going to the university, and count the number of people whose age is 20 going to the university, age 21, you will see a lot of them. They were picking up like this. So this is what you call distribution. Your histogram is where your distribution is, and this is how your data is going to look like. This is the pattern that you're going to see. Okay, wherein there is a peak in there. So this is a very powerful this is a powerful uh, distribution to study. So we're studying this now. Okay. Okay. So normal distribution, I'm going to take a look at this is governed. There's a table for this, and this table is going to come up later on. Then there is also another one, which is related to the t distribution. Sorry, normal distribution, and that's called the t distribution. Okay. the t-distribution is similar to the normal distribution. And when do we use this? Well, when we use the t-distribution, which is like a normal distribution, when the standard deviation of the population um, um, is not known. Okay, so if the standard deviation, when the population standard deviation uh, is known, we can use the normal distribution in our work. Often this is not the case. So we will rely on the student t-distribution to help us move on. In other words, most of the time we don't know the population information, correct? Because we're sampling. And when we are in that situation, then hope is not lost. We can use the t-distribution in our subsequent methods, which we will show you later on, okay? So it looks like the normal distribution. And the only thing different between the normal distribution and the t-distribution is that in the normal distribution, you get um, there is no such thing as a degrees of freedom, or the number of samples do not come into play, okay? In the t-distribution, which we will study later, the number of samples come into play, and we will find out, we will have to get some information about our sample and the so-called degrees of freedom, and we will compute that degrees of freedom, which is n minus 2. Okay, we'll talk about that. Okay, let me proceed further now. Okay, this is how a t-distribution looks like. You can see now this is the degrees of freedom. And later on, we'll talk about that thing called alpha area. If you compare it with the Z distribution, here is the value of your Z, of the distribution of your data. And in here, we have the value of our Z that matches the area of probability, okay? So we'll talk about that later on. But just to let you know, there's a slight difference between the t-distribution and the Z distribution, insofar as the degrees of freedom is needed in the t-table, okay? But you can see it's the same, okay? It's the same shape, okay? All right. So let's talk about the notion of confidence interval now. Okay, so 8:30 I started. I should finish at 10. Okay. All right. So the notion of confidence interval. In the notion of confidence interval, this is an interval that we like to estimate to know where is our mean located, in what range, can we confidence, I mean, it's a confidence interval. We are confident to a certain degree that the mean of the thing that we're studying falls in a particular range, okay? Falls in a particular range. So we're going to talk about that, okay? Now, we have two informations now, okay? We have the normal distribution, or either the t-distribution, which is found in nature. Most of the time you will encounter this, okay? And then we go now to the second idea. Second idea is called confidence intervals. We want to know, for example, what will be useful to us. For example, now in the student example that I get, okay, we want to guess. Okay, we know we will see a lot of people whose ages 18 going to the university. A lot of people going to the university whose ages 20, 21, 22, 23, 24, 25. Okay, in that range, okay, all right, 18 to 25, maybe 26, okay, for our particular university, we want to know, okay, what is the average age of students in our university taking a bachelor's degree? Okay, so we like to know 95% of the time, okay, we will find the mean, the average of our, I mean, average there we don't know, okay, because we only have the range, but perhaps the average for our particular so-called university, it might be 22, okay, it might be 23, okay. So, but we want to put it into a range so that we know that within this range, we are 95% sure or 99% sure that the mean is in that, it's inside that particular two values, the upper and lower values, for example. Okay, so we will have a notion called CI, or level of confidence. To form the confidence interval, we need to specify a level of confidence in terms of percentages. And it goes like this. It looks like the confidence level is equal to 1 minus alpha. Okay. And this alpha is subjective. We specify this alpha. Okay. This alpha is what we call the critical value. Okay. Because when we subtract this alpha from 1, okay, 1 is 100%, in other words. Okay. Uh, if we want 95% level of confidence, in other words, we're 95% sure of that most of the time. Okay, if we take samples, 95% of our samples will get the um, mean within our sample. Okay, well, we're looking at 95% level of confidence. This is the normal. This is usually what's used by statisticians. We want to be 95% level of confidence. And so here, our alpha will be 0.5%. Okay, so we divide our, because it's an interval, we want our the range that we're talking about is 95%. So if we look at the probability distribution, which is normal, we will have this level of confidence in that our sample mean is within this area. It is going to fall inside this area here. Alpha is called the level of significance. Effectively, we have an upper limit and a lower limit. And this is, when you measure that upper limit and lower limit, it's 95% of the area here is the probability where the parameter, when we mean parameter, we mean the mean or standard deviation lies. Okay. So forming the CI for mean, which with unknown standard deviation. Okay, so here's one example now. Okay, when the number of samples is big, like n is equal to 30, we can always use the normal distribution. When the mean is when the standard deviation is unknown, okay, and we have n less than 30, okay, then we will use the t distribution. Okay, so here when n is equal to 30, bigger than 30, we will use the standard deviation, sorry, the z distribution to do the hypothesis testing. Okay, so let me now first, before I go there, let me just get to my um, I'm just going to draw you a diagram, okay, a whiteboard. Can you see my whiteboard? Can you give me a yes or no if you can see my whiteboard? Yeah. Yes. Okay. So this is okay. Let me. Okay, here I'm just going. Okay, there it is. Okay, let me just. Okay, this is the real world. We're always looking around the real world. Okay, this is the real world. Okay, here's our phenomenon. We said we can confidently assume it is a normal distribution. Okay, because we phenomena. Okay, but the mean here is a certain amount. Okay, okay, and its sigma is a certain amount too. Okay, this is where we're doing the sample. This is where our sample, we are sampling here. This is the real world. So what happens is hypothesis testing is that in the sample, in the real world, we go to the Z world. Wherein we know that the mean there here, the mean is always equal to 0. And here, the standard deviation is equal to 1. Okay, so we take the real world, go to the Z world, make conclusions in here, so we make conclusions in here, and whatever we conclude there, okay, we bring it back to the real world. In other words, the conclusions we make in here are true. What conclusions we make in here will be true in the real world. Even though, so what we do is we take samples in the real world, bring it over to the Z world, okay, make conclusions there, and whatever we conclude here, it's true over there. Okay, so this is the reason why now, when you go in here, and you notice in here, notice there's a 0 there. Okay, because this is where we're going to go. It's a mapping. Okay, whatever we conclude in here is going to be true in the real world. Okay, so going further now, got 30 minutes to go. Okay, so the formula for a confidence interval, if you want to get a confidence interval, is take your sample, take your standard deviation, which is, this is not, of course, your sigma, this is S, this is approximation of your sigma, your standard deviation, okay, of the sample standard deviation, and divided by square root of n, the number of samples you have. This is how you form it. Your Z alpha over 2 is your confidence interval, okay, and over 2 that you put in here. In other words, if it's that's going to be, normally it's 1.96 because they put it at 0.5, but you can change that if alpha is equal to, okay, you want it to be more stringent, okay, so you want your alpha to be wider. I mean, the CI is wider, you can have it at alpha is equal to 0.01, for example. That's 99% confidence interval, okay, so that's what you're going to put in here. That the 1.96 there is what you're going to put in here. So where do you get that 1.96? Okay, if you look in here, now here we're going to use the table, okay, but in R, that's going to be given to us by the R package. Okay, alpha is equal to 0.9, 0.25. Okay, that way we read this is 0.95 is what we're going to look into there, okay? So why is that? This is the probability, the area of under the curve, okay? That's a probability measure of under the curve, okay? So here, we look for 0.95, okay? And it's almost like in here. 1 point here. Sorry, that's 9.6, okay. So the probability there, we're looking for the probability in this area here. We want that to be 95 plus 0.02, okay? So eventually that will match here. 1.96. Okay. So why would it match 1.96? Okay. You look at this 1.96. Yeah, there you go. Why? Well, because this is from here to there is 0.95. You got an area here to the left, which is 0.025. So you add that together, that will be uh, um, uh, 0.9750. Okay, so this is where you go. So 1.96 is where you get that. That's your interval. Okay, that's why you get this there. And therefore, that's what you're going to use in here. You calculate this, your x bar, your s, under divided by n. Do the same for the other one. This time it's a plus. And then you get your confidence interval. So now here, let's draw a 95% interval on the Irish data set on the sample length. It's available in your R installation. You just have to change this, okay? But if you try this, you can see that this is found in your, okay. Let me give you the actual code there. This will be your CI.R or CI normal, okay? Let me just get that. So let me know if you can get this in your code. Now, this is your Irish data set. And try it, you can get your confidence intervals for your there, okay? The confidence interval is 95. Oh, sorry. Um, I'm can you see this? Can you see my R code or no? Let me know if you can see my R code. This is called CI normal.R. So I'll type it through. The code there is ci.normal.r. So for Irish data set, how many of you are familiar with the Irish data set? Everybody familiar with this? This is the data set that's got sepal length, and this is a flower. It's got the length and the width of the flower of the petal. Okay, so all right, I understand. I thought my mistake, but you can do data. Let me tell me if you can see my code, okay? I'm going to go to my code now, and I'd like you to tell me if you can see my code. Can you see my code here? Okay, I'm just gonna go to my, can you see my code? Okay, I'm just gonna go in here, okay, to my code. I'm gonna go to my SARA. I'm just gonna tell him just to make sure my working directory is file Spain, okay. And let me try and run this. Okay, so you got there, okay? So it picked up this. What's the Irish data set? I'm going to type it through now, okay? Okay, this is the Irish data set. The Irish data set is the famous Fisher or Anderson Irish data set, gives the measurements of centimeters of the variable sepal length and width and petal length and width, respectively, for 50 flowers from each of the 3 species of Irish, the Irish flower. The species are Iris setosa, versicolor, or virginica. Okay, this is for, okay, so if you look in there, okay, so we can do a view. I'm just going to give you an idea what this what is it supposed to give me that? Yeah. Okay, let's try to get the, okay, here it is. Okay. I don't know why it's taking a long time to show you, but this is the Irish data set. It's got no. No. This is okay. All right. So that in here we're studying the what we wanted to get the length, the sepal length, okay, of the flower. So here we're 95% sure that the mean of the sepal length is between 5.7 and 5.9. And here, okay. So there it is, okay? This is the length. So let's do the mean. I'm going to show you, I'm going to prove to you that the mean is between 5.7 and 5.975. Okay, can I do that? Okay. Let me tell you, let's confirm that it is between that, because we're 95% sure that the mean is going to be in that range. So let's prove it to ourselves that it's going to be inside that range, okay? So we'll just do this. And we just get sepal length. That's all that we want. Okay. That's all that we want. Voila. It's 5.8433 in between 5.71081 and 5.97584. How many of you say yes? Just want to make sure that this is driving the principle to you. We wanted 95% confidence that the mean is in between these two numbers, and then we calculate the actual mean, okay, to prove to ourselves that the statistics is working, and we're correct. 5.84 is indeed between the high value and the low value of the confidence interval. Okay, now how this will now come into play when we do our testing of hypothesis. So there R produce our low limit. This is the low limit, okay, and the upper limit, okay. We want 95% confidence, okay, and it did give it to us. On the other hand, now when we forming a CI for a mean with the unknown is similar, okay, but this time we're just going to do the T distribution rather than the normal distribution. So I have an example here, okay, but maybe it's best that we do this last because you want to know statistical testing of hypothesis right away. I want you to keep this thought for a minute, and I want you to expect that we're going to ask you to do this exercise. The data below represents an annual account fees for checks made by a bank, for example, 23 clients, okay, with check accounts who do not undertake internet banking. Get a 95% confidence interval for the mean of this. And then also confirm that the actual mean is in between those two numbers that you're going to get, okay? So I'm just trying to go to the time now, okay? So here is an example. The bank cost, okay? So we did the whole thing with the X bar, we did the S and the number of samples, we're alpha here, in the area here. And then we have the margin, okay? We're looking at the margin, the X bar minus the margin, and X bar plus the margin. Similar to this one, okay? And what did it say? Okay, that our low limit, we expect the mean to be 21, between 21.03 and 25.05 of what? Well, this is the bank cost, okay? The account fees, annual account fees of people in the bank, okay? For a sample of 23 clients, okay? So here we did this, all right? And so what happened? We could try to confirm the actual X bar, okay? And we know here, it's $23.04, okay? What's that? Well, that is in between the low limit and the upper limit, okay? So this is a practice that we're going to do. Change it to 90%. Did the interval become wider or narrower? So I'm going to ask you that question. So here now we go to testing of hypothesis. CI is prelude to the idea of testing of hypothesis. Okay, this is how a scientific idea is tested. If it should be believed or doubted. Okay, this idea is also called statistical inference, wherein we deduce from a sample to the population. Now, even if you don't know a lot about hypothesis testing at the moment, the fact that you can grasp the concept of confidence interval, that knowledge will lead you to getting a good knowledge of testing of hypothesis. So even if we finish off the day today, all right, okay, we didn't get too much this testing of hypothesis, but you know this confidence interval, then having a knowledge of this and using this to springboard to testing of hypothesis knowledge will be useful and help you. But let's go to it anyway. Usually, testing of hypothesis involves the estimation of a parameter of a distribution. That's the reason why we're talking about a probability distribution, okay? Usually and often, we are trying to estimate a mean, okay? I mean, I'll give you an example. Let's give the example that you are, okay, let's give an example that you are a pharmaceutical company and you claim your laboratory people that's working on a vitamin, okay, like an omega-3 vitamin, is going to make a claim that, hey, by using this omega-3 vitamin, we can lower down your cholesterol to 50% level. That's a claim. This is where your testing of hypothesis is going to come in. Is the lab people giving you the right idea? Are their vitamins that they're producing going to do what it's supposed to do or not? Okay, so here are the steps. State the hypothesis. The way we state the hypothesis is that we state the skeptical view, the HO, the null hypothesis. The reason why it's called the null hypothesis, we have two hypotheses that we're going to put in. One is called the null hypothesis. The other one is called the alternative hypothesis. If the pharmacy is making a claim that is going to lower down your cholesterol by 50%. The null hypothesis says no, nothing is happening. So in other words, no. In other words, the amount of this is the skeptical view. The HO is always the skeptical view. That's not your. We say no. Your process is not correct. Okay, it's not going to bring it down. So in other words, null meaning status quo. HO is so there is no change. In other words, your mean change is equal to 0. That's why it's called null. So it's how we formulate that, okay? The alternative is, there is your alternative, is HA is that your difference in your cholesterol will go down by 50%. It's going to be less than 50%. The difference is less than 50%. That's what you're going to be doing, okay? So this is what we are going to do. The null hypothesis is still the same, 0 difference, okay? The alternative hypothesis is there is a difference. Always the null hypothesis is the skeptical view. Whatever process you're doing is not going to affect any change. That's why null means no change. That's why it's called null. Then the second procedure is choose a level of significance. What value are you going to use to become sure? Normally it's 95%. Level of confidence, okay? Level of significance is alpha equals 0.05 here. If my confidence interval is 95%, alpha is 0.05, okay? Select the appropriate test statistics. What are we going to use for our sample? Well, if we have a lot of samples, it's normal Z. If we don't have a lot of samples, we'll use T. Only 2 choices, okay? And then the next step, determine the rejection region, okay? And then after we determine the rejection region, okay, where is that? Okay, well, the rejection region is found here. If we're using the Z statistics, okay, your table tells you this. This is your region of rejection, okay? In other words, if we're going to compute a Z value, if our Z value falls in that region, red region, okay, then we will reject our null hypothesis. That's the reject region, meaning say, look, your null hypothesis is rejected. In other words, there was a change, okay? According to the samples, there is a change that happened, okay? So that's what we're going to do. When it say reject, we're going to reject the null, okay? And what does the null say? Well, the null says there's no change. Well, we reject the null, it means there is a change, okay? So that's the next step, is to find where this region is, okay? This region is something that you specify. We'll just look at it in the graph, okay? So now we collect the data and calculate the value of the test statistics, make N as large as practical, and then state the decision and conclusion. Those are the steps, okay? So what can happen? Okay, well, there are certain things that can happen. You can be rejecting HO hypothesis when in fact it is true. Okay, this is called type 1 error. We're saying HO reject the null hypothesis, meaning to say we're taking the alternative as correct. Okay, but in fact that is true. You rejected that something that's true. Okay, that can happen. This is called what they call type 1 error. On the other hand, HO is accepting HO. We're saying there's no change when in fact there was a change. This is called type 2 error, okay? So this is, the graph here is called the critical value, critical region, or region of rejection. We have it there, okay? The p-value is the probability of getting a test statistic more extreme than the sample result, okay? Given that the null hypothesis is true, okay? So what is the p-value that we're setting? The p-value is a value that we want to compare with our alpha, okay? And the p-value is saying uh, this is the probability of getting a test statistic more extreme, more unusual than the result. In other words, rare. Okay, this is the probability you're getting a rare, unusual result. Okay, when the HO is true, you want that to be very strict. Okay, you want to be strict because given that the null hypothesis is true, if it's true, okay, you don't want to reject what is true, right? So you want that to be stringent. In other words, this is a probability that what you got is extreme. In other words, this is not, if it's small, you want that small. If I make the probability of 0.01, for example, that means to say the probability that my sample is very rare is 0.01. In other words, this is typical. Okay, your sample is typical. In other words, if your sample is typical and you are falling in that range, the reject region, you reject HO, okay? Because your sample is not unusual, okay? Okay, so because you're just setting the p value is the unusual value, okay? So you want that to be small, okay? So here's an example, okay? Here's an example of testing of hypothesis, okay? So the approval process of a life insurance policy requires a review of the application and the applicant's medical history, possible request for additional medical information and medical examination, and the policy compilation stage where the policy pages are generated, then delivered. The ability to deliver approved policies to customers in a timely manner is critical to the profitability of this service. During a period of 1 month, a random sample of 27 approved policies is selected, and the total processing time in days recorded. Now, I don't know if you work with insurance companies, through the customer likes it to be, the processing days to be smaller and smaller. You want your money right away when you make a claim, okay? Or if you're going to, this is approval process of giving you an insurance, you want that to be delivered right away. Okay. In the past, the mean processing time averaged 45 days at the 0.05 level of significance. Is there evidence that the mean processing time has changed for 45 days? Now, I'm going to ask you this question. Okay. Now, what is the null hypothesis? You can type it there. I'm just going to give you 1 or 2 minutes. Okay. What is the null hypothesis? Clue. The null hypothesis, there's no change. What you're testing, you're testing the mean to be equal to what? How many says 45? How many says more than 45? Where there's no relation, okay? So I'm asking the question, how do you formulate your null hypothesis? Knowing that the null hypothesis is asserting there is no change. Okay? All right, I'd like you to answer it in your mind, and then I'm just going to count in 10 seconds, okay? And I'm going to put the answer. Okay, what about the alternative hypothesis? Okay. Yeah, Komal, that is correct. Yes, that's also correct. The mean is not equal to 45. There's a change. Alternative is always there's a change. The null hypothesis always there is no change. Now, how are we going to decide this? We're going to calculate the t statistics, okay, and find out where it lands. Where do we land? Okay, is it going to land in our our area or not? Okay, so here we have to look at the degrees of freedom. Sorry, degrees of freedom is n minus 1 degrees of freedom. Okay, so if this is 27, our degrees of freedom is 26. So here is the testing of hypothesis code. Okay, and here we have this is a very important um, uh, algorithm or rule. If your p-value is greater than your alpha, okay, in other words, it doesn't fall inside, okay, accept the null hypothesis. We have no strong evidence to reject null. On the other hand, if it's your p-value is less than alpha, in other words, it's going to fall into the uh, reject area, we reject the null in favor of the alternative. Okay, so so the answer here that I got right away is that uh, uh, reject the null. Okay, and so let me run this and see whether you can find out this part here. Okay, so with us, where is that? Let me run this. Okay, where is that? Oh, okay. One test, t-test. Okay. The p-value is I don't know why it's giving me error result. P-value if uh, p-value is greater than alpha. It has length greater than 1. Oh, okay. I'll find out. Okay, but the conclusion is correct. Okay. So this is our data. We picked it up. We pick up the insurance CSV file. Okay. We do a test data. My data alternative is greater. Mu is 45. Okay. This is the null hypothesis basically. And our alpha is 1 minus result confidence interval that integer, okay, which is degrees of freedom is 26, okay, and p-value is 45.5894, and the p-value is big, okay, that we get. So we have to accept the null hypothesis, okay? Because its alpha is bigger, okay, than our alpha. Our alpha normally is 0.05 here. And so we have to accept it. In fact, this is what I got. I don't know why it's getting that. That's what we got here, okay? We have a strong, this is the thing that happened here. This is the accept the null. Don't know what's happening. So anyway, but if you look into the data, that's bigger than our alpha. Our alpha is 0.05. Okay, this is bigger. Okay, and if you look at the t, it doesn't fall inside the. It's going to go to the left. Okay, the mean is 43.88. Okay, that might say that is different from 45, it looks like, but the confidence interval says that's where that we're still in there. Okay, so so this is correct. Okay, according to our data, the data is of course supreme, and according to our data, we should say, well, there is no change except the null hypothesis. Okay, so that's what we should be doing there. So that's how we do the, see, it's very small. Okay, this code is very small to do your testing of hypothesis. You grab the data, take the data, and then of course give the alternative is greater. What is the mu that you're looking for? It's a t-test, we said that, and then it's you can see here already what's being calculated for you. You say, well, that p is greater than alpha. Okay, accept the null hypothesis. So that's where that's so easy in R. The code is very small when it comes to R. And here, I still have about 2 minutes. Okay, so in here, I can, if we go to our alpha, okay, so degrees of freedom is 26, it says here. Let's look at 26, okay, and our degrees of freedom is 26, okay. Here, with an alpha of 0.025, you need to go 2.055 there, okay? And we are negative 2, which is over here to the left, okay? Which is, so we are not in the, inside here. We cannot reject the null hypothesis. We're way to the left, okay? So there's the 26. We look at the degrees of freedom. And our probability that we got is 0.05 something. So it's over to the, even to the left here, okay? So it's way to the left to here. So we cannot reject the null hypothesis. We're not falling inside that, okay? In order to fall inside that, we should be to the right of 0.025, okay? Because that's where it is. And we're going to be 26. In order to reject that, we should be around here. Our t has to be around here. Something like that, okay? So that's what we're saying. So in other words, going back again, we did a small exercise. I know you need more exercise to do this. So, but we're running out of time. It's going to be a bit harder to do everything in 1.5 hours. But I hope I could clarify some questions for you. If it's time for questions, I leave it to Dr. Ajay if he wants me to answer questions that will help you.
Thank you, Lito sir. Actually, the issue is our students are very, very beginning stage of statistics. And you gave an awesome presentation. And I hope when they will self-study, hypothesis testing, and after that, when they will watch this video again, it will be extremely helpful for them, right? So, but thank you so much for giving us such a detailed session for this. And I request to the participants if they have some feedback or questions, so they can ask. Actually, I thought to take it for one more, but by seeing the energy level of the participants, because it's the 4th day of the summer school and they are literally exhausted, and one more day.
That's right.
Yes, and we know that statistics is heavy. It takes a toll
It's
on
heavy,
the body
yes.
and the mind. Yes, and but somewhere we have
Correct.
to start, and your session will help us to pick up statistics, especially hypothesis testing, which is a very, very interesting and important topic. And on behalf of SARA team and the students, we thank you, Dr. Lito Cruz, sir, for taking a session for us on the hypothesis testing. And we left with one more
One more.
session that was regression and forecasting. I humbly request you, sir, we reschedule that and we will do it one maybe in coming months sometime. We'll fix a time and we'll do it online.
Okay, no worries.
Yes. So
Yes.
thank you so much for attending this session. And
Thank you for having me.
sir, and thank you all the participants.
Okay, thank you.